This is Hongjian Zhou from Arizona State University. Our group scope is led by Professor Jiaqi Gu. I'm glad to share our recent progress in photonic design automation, LiDAR, automated curved waveguide detail routing for large-scale photonic integrated circuits. First of all, I want to highlight what makes photonic detail routing different by showing some specific rules in PIC. In electrical routing, the target pin can be accessed in any direction if only the wires are touched with each other. Meanwhile, in PIC, we have ports that are connected by waveguides. These waveguides have to precisely align the ports during final access according to the port orientations. Besides, sharp turn in PIC is prohibited, and there is no minimum band, and there is a minimum band radius constraint. Usually, the PIC only has a single routing layer. A crossing component is needed when a waveguide has to cross another waveguide, and this crossing component is area consuming. Regarding the signal integrity, waveguides have different wave cross-section and material carrying different modes of light and should be matched correctly. Therefore, with all these constraints, PIC layout heavily relies on manual design. But manual design is time-consuming. In PIC, the optical part is treated as separate instances, such as segment, banding, and crossing. Each is a device in the photonic circuit. And the designer has to place each instant carefully, considering the band radius, spacing, and alignment constraint, etc. Therefore, these instants are highly relative and need back and forth modification, killing a lot of time. So this method only works for small scale circuits. But PIC scale and design complexity grow rapidly. The number of instant nets grow from tens to hundreds, and the design is from well-structured line modulator microring wideband to irregular large-scale photonic tensor core with more and more stringent design rules, which is hardly handled by human. Therefore, auto detail routing tool is needed to increase productivity and reduce time to market. Then it comes to quality metrics to evaluate the routing solution. The maximum insertion loss among of the part insertion loss in the system, which is very important metrics in photonic circuit. It tells maximum power loss when the light goes through the system. So it determines the needed laser power. The path insertion loss consists of inherent device insertion loss and net insertion loss. A path may have multiple devices and net alone its path. And the net insertion loss consists of the propagation loss plus banding loss and the crossing loss. The total net insertion loss is given by the path length, the total banding angle, and the number of crossings along the path. So our problem is given a set of nets and place devices, generates routing solution for each net, then the final maximum insertion loss is minimized. There are already some works for PIC routing, but most of them focus on global route planning, especially on optimizing the crossing. But these methods overlook the physical implementation of the path, which may lead to path congestion and crossing insertion failure. And this solution is not final GDS layout. And there are also some work on detailed channel routing, where the problem is reduced to a channel routing problem, but it will be no room for further crossing optimization. So in addition to minimize the maximum insertion loss, we should also be fully aware of physical implementation and design rules so as to reduce the back and forth modification. Then we propose our solution called a LiDAR, which can generate curved waveguide while honor the crossing and banding constraint. We solve the problem by answering these three questions: how to find a path that is physically implementable, and how to mitigate routing congestion on a single layer, and how to optimize the crossing. To generate curved waveguide, we augment standard A-star search algorithm, in which the path searching process is driven by the cost function. In the A star, in the standard A star, it only explores the direct neighbor of the node, but here the neighbors depend on the current path, direction, and band radius to satisfy the minimum band radius constraint and line orientation constraint. Therefore, we extend the A star node state to remember orientation. And based on the node coordinate and its orientation, we refine the node's neighbors, which are adaptively calculated based on the given radius and grid size. But before we explore the neighbors, we should check their legality first. Here we propose the oriented grid map and track all the grids from current node to neighbors. These grids are assigned with type attribute based on the routing waveguide, orientation, and the blockage. This oriented grid map not only ensure the basic spacing requirement, but also enable correct access direction and crossing insertion. When the neighbor candidate doesn't hit anything, then the neighbor is legal and added to the priority queue. If the neighbor hits target node, then check the neighbor's orientation to make sure correct access. When the neighbor hits other routing nets, then we should check whether we should add a crossing there, including the current segment's length, orientation, and the waveguide type and needed space. Only when all this satisfies, we can cross the routing waveguide, and the neighbor will be treated as not legal for other cases. Currently, we just finished one single net routing, but when it comes to multiple net routing, there will be waveguide conflict problem due to the high port density and waveguide blocking. For example, if the net J pass near port region of net I, hardly the net I can connect the target port. So we need to dynamic reserve space near port before that. If the port is located in the cell, we should propagate it to the boundaries first. Then the grids in front of the port can only be used by that port, and it will prevent other nets from crossing this port region. Second is uh, there if some ports share the same grids, then we will spread these ports and assign them to new ports without congestion. Apart from the port, there are also conflicts between waveguides, especially for the component with high port density. Without carefully planning the routing waveguide, will easily block other nets. The waveguide connects to those ports are usually close to each other. When some other waveguides have to cross this waveguide, there will be not enough space for putting two crossing consecutively. Observing that the waveguide space is usually defined by the final access port, we set some offsets among these ports so as to supporting consecutive crossing insertion. Then we propose group-based net routing order. Observing that ports with the same orientation in one cell usually have similar routing topology, these ports are grouped together, and only the ports in one group are routed. The framework will proceed to other port group. Within the port, the nets are routing in clockwise order. Besides, we add the group-based congestion penalty to reserve routing resource for unrouted net. To further optimize the crossing, we need to find out why crossing are introduced first. There are three reasons that if a path uses crossing. The path obstructed by other net, high congestion penalty, and non-detour without crossing. So if the solution do not use crossing, the result will be safe. Otherwise, non-crossing routings will be activated to find the reason of crossing. If the NCS fail, it means the net is obstructed by other net. If the blocking waveguide never be reported before, it is highly possible that it is caused by inappropriate net order. Then we report the blocking waveguide and reroute the current net. If the non-crossing solution success, then we will save the solution with minimum insertion loss between them. Finally, let me show our LiDAR experiment results. We test our framework on the photonic tensor core and wavelength routing optical network on chip benchmark, and the device insertion loss are given by this table. We compare our LiDAR with two variants of proton. The first one is equipped with report route, and the second one active with diagonal neighbors. Regarding the maximum insertion loss, the LiDAR is 40% better than base 1 and 5% better than base 2 on average. And our LiDAR can generate DRV-free solution on all the benchmarks, while other baselines cannot. And LiDAR much faster than base 1 and base 2 on average. Here, here show the animation of the intermediate routing result. So after all the nets are routed, we will instantiate the route crossing first, and then the connected waveguide. And this animation shows how we optimize the necessary crossing here. Finally, I want to show our LiDAR's capability of handling different crossing parameters, alpha C, and evaluate the effects of group-based congestion penalty. The higher the crossing parameter, the lower the crossing number it will give. And without the group-based congestion penalty, the DRV is introduced when the alpha C is 0.3. Now, let me conclude our work and give future direction. LiDAR is an open source automated detail routing tool specifically designed for photonic integrated circuits. LiDAR feature a non-Manhattan carrier-aware A-star search engine with accessibility enhanced port assignment and adaptive crossing insertion, construction-aware group-based net ordering and objects, and a crossing optimization scheme to handle unique PRC routing constraints while optimizing critical path insertion loss. In the future, we will honor more routing constraints and accelerate the algorithm using C and C++, and test the network, test the framework on much larger benchmark. So that's all. Thank you.